Hello class, welcome to lecture 24. This is the first lecture in the final sequence of the course, whereby we turn our attention to the most nonlinear sorts of behaviors we can imagine tackling, those associated with phase transitions, which are truly singular responses, as we will articulate later on in this lecture. Before we get there, let's just do a quick review of what we talked about most recently. So most recently in lecture 23, we wrapped up our discussion of reaction rate theory. So we had, over the course of a few lectures, worked out a theory for simple unimolecular processes, A goes to B, in which case that rate could be written in one realization as a so-called flux side correlation function. A correlation function that was predicated at starting at some barrier, some transition state, call it Q star, correlated the flux over the top of that barrier with the probability of being in the reactant state, and a way to then encode the probability of getting to that transition state would be to multiply it by the Boltzmann factor associated with the likelihood of fluctuating to that transition state divided by this length scale L, the characteristic width of the A basin that you're starting in. Within transition state theory, this could be rewritten concerning only the zero time part of that correlation function, giving us a thermodynamic estimate of the rates. As that's an approximation, there's a correction factor in principle, the so-called transmission coefficient, that we worked out various theories for, which encode dynamics that occur at the top of the barrier. Last lecture, we talked about generalizing this perspective to bimolecular rate processes, in which the rate in principle depends both on the likelihood of some reactive fluctuation occurring, overcoming some transition state, but in addition, those two molecules, A and B, have to find each other to react. And so it also depends in general on the diffusion constant for which they go through space with. So the reaction diffusion rate constant, the bimolecular rate, depends in general on the diffusion between A and B, call it capital D, as well as a length scale lambda, which is the characteristic length over which A and B interact with each other. Given by an integral over the Boltzmann factor of their interaction potential divided by r squared. And in the denominator of this fraction is the intrinsic rate with which A and B would react, provided they were close enough to each other to react, times the probability of finding them at that position. So various limits when D is very large or when K star is very small or very large results in so-called diffusion limited or reaction limited kinetics. Very generally, we also briefly discussed an alternative perspective to rate constants as given by ratios of path partition functions, summing up all reactive trajectories that go from A to B, dividing them by the sum of all the trajectories that just start in A. as a ratio of partition functions, even in a path space. This has an interpretation as a reversible work, in this case, the reversible work to transform an ensemble of trajectories from ones that are just conditioned to start somewhere specific, like A, to ones that actually traverse a barrier connecting a set of reactants A to a set of products B. Okay, so that was a realization of a dynamical process, a nonlinear dynamics. A barrier crossing results from far excursions away from the typical states that a system explore. Nevertheless, equilibrium theories work very well because the fluctuations that get those particles to the top of those barriers are still thermally mediated. So while it's a nonlinear response, a nonlinear process, it's one in which equilibrium statistical mechanics is capable of working out pretty thoroughly. So for the rest of our course, we're going to turn our attention, as alluded to already, towards very nonlinear behaviors, though those associated with static response. In fact, the most nonlinear response one could observe in a molecular system is associated with a phase transition. So today we're going to take a little bit of stock on phase transitions, concerning mostly just the phenomenology of phase transitions and some basic results that are known. This will serve to motivate a theory, the so-called Landau-Ginzburg theory of symmetry breaking, which underpins the modern understanding of phase transitions. So we will work out Landau theory explicitly next lecture and use it to uncover some basic properties of phase transitions. But for today, we're going to spend most of our time just talking about phenomenology. All right. So just to get us all on the same page, consider a phase transition that you all have common experience with. Imagine you took a beaker, you put it on a hot plate, which let's imagine is really heated by some little flame. I know that that's not exactly how hot plates really work, but for all intents and purposes, that serves the purpose. So there's our little flame. And in that beaker, let's fill it with some water. And now if we were to monitor the density of the water in that beaker as a function of the temperature, so stick a little thermometer down in there, what would we see? So at low temperatures, before I started heating it up, the fluid would be fairly dense. Most fluids expand upon heating. That's true even for water, as long as you're above 4 degrees Celsius. And so the density would go down. But what happens? Would the density continue to just go down continuously for all temperatures? No. We know at some point you start losing water. And in fact, You all know that when your kettle starts to whistle, that's because you're starting to vaporize that water, which is abruptly changing the density from that associated with a liquid, a condensed state, even this is misleading, to something which is much, much less dense, a vapor. That happens at what we call the boiling temperature. A reasonable question would be to ask, well, how sharp is this transition? Does it occur over some finite amount of temperature with some finite epsilon? No. We all know that this is infinitely sharp if we were to really wait for the system to equilibrate. If I went epsilon to the left, I would, for all eternity, have a stable liquid state. I went epsilon higher than the boiling temperature. If I waited a long enough time for the system to equilibrate, I would discontinuously change the density to that associated with its vapor. So that, if we were to imagine temperature as an external parameter, I am finding, as I go through the boiling temperatures, I take the liquid to the vapor, a singular response to an applied temperature in the vicinity of this boiling point. So that's what we mean by a phase transition, here liquid going to vapor, being associated with a very nonlinear response. In fact, it's so nonlinear, it's singular. There's nothing particularly special about a liquid to vapor transition. If we were to take a simple magnet, some north and south pole, for which I could measure its magnetic moment and apply an external magnetic field for epsilon positive, I will create that magnetic moment pointing in the direction of the field. For epsilon negative, I will point that field, the magnetic moment, in the opposite direction, again, thermodynamically speaking. And there's an infinite susceptibility associated with that magnetic moment as I apply an external magnetic field. Again, a singular response to an external parameter. If you thought about this for a moment, it's a very peculiar thing to have happen. A phase transition is so commonplace in our everyday life, freezing and boiling especially, that we forget just how odd it is that a system of atoms and molecules could actually undergo such abrupt change. This is meaning, if you were thinking about it in terms of atoms and molecules, that over an infinitesimally small parameter change, the molecules are able to coordinate a macroscopic response, flipping all of the spins in an entirely, in a macroscopic bar magnet to point in one direction or the other, losing all of those liquids' neighbors to instantaneously go from a dense state where they are favorably interacting to a dilute state, where rather the entropy is maximized. So not only is it odd from a molecular perspective, it's odd from a mathematical perspective. As we know from introductory statistical mechanics class, any observable, like the average magnetization or the average density, is at its heart computable from a partition function. Those partition functions might be complicated to do, to actually evaluate, but we know that in principle, if we could take an appropriate derivative and evaluate the average magnetization or density. A partition function is always some sum of weights. In a canonical ensemble, this would be a sum over Boltzmann factors. Where that potential depends on a particular microstate, and that microstate might be complicated if there are lots of atoms and molecules with lots of degrees of freedom. But the mathematical structure of the partition function is one in which the exponential away from t is equal to 0 is a smooth function. And a sum of exponentials, or a sum of smooth functions is a smooth function. So Q, its parametric dependence, the partition function's dependence on control parameters like beta, seemingly must also be smooth. So for example, if I were to take a derivative of log Q with respect to minus beta, I know that I should get back the average energy if I took two derivatives. I should get back the fluctuations in the energy, which is proportional to the heat capacity. So those quantities must be smooth. And yet we know that as I go through a liquid vapor transition, the heat capacity, for example, changes abruptly. It goes to infinity. We know that the internal energy changes discontinuously as you boil off a liquid, resulting from the instantaneous change of the molecular environment from one in which you have attractive adhesive energies that act to condense that liquid, to a state in which those attractions are completely gone and you're left with just kinetic energies. So what gives? What's going on? Is the mathematical structure of statistical mechanics just incapable of describing phase transitions? Q being a sum of smooth functions, implying that its derivatives are smooth, making it impossible to get a discontinuous change in something like a energy or divergence in a heat capacity. Do we need a new theory, or is there a loophole? Well, it turns out there is a loophole. While it is definitely true that a sum of smooth functions is a smooth functions, there's one corollary, which is that sum is finite. If one has an infinite sum, that need not be smooth. So if I have an infinite number of particles, I would have an infinite number of microstates, and thus only in that limit could there be a discontinuous change in the partition function. So this is an important first lesson of the phenomenology of phase transitions, which is that they only strictly exist in the thermodynamic limit of an infinite number of particles. So phase transitions as real discontinuities to which you say, well, no system really exists with an infinite number of particles, but Avogadro's number is sufficiently large that the deviation from an idealization of a phase transition being truly singular from one which is very, very close to singular is essentially academic. However, that is a necessary condition for a singular response. It doesn't mean that just because you are in the thermodynamic limit, you have singular responses. If I had an infinite number of ideal gas particles, their density temperature relationships are smooth functions. Moreover, if I imagine taking a system, blocking it up into subregions, which are macroscopically large, or at least mesoscopically large. Imagine I take my beaker and break it up into cells that are millimeters in size. If this is a fluid, for example, all of those cells are identical, I can assign a partition function for the specific region, call it Qi. If those cells are macroscopically large, I might be tempted to say that each cell is non-interacting, so I can compute the partition function as as a product of these single cell partition functions raised to the number of cells in. The derivative of the log of Q with respect to beta would be n times the derivative of log of little q with respect to beta. Little q has a finite number of degrees of freedom. Even in the limit that n goes to infinity, that derivative would be finite. So if I have a system for which I can break up an infinite number of degrees of freedom into non-interacting subregions, such that their partition function factorizes, the additivity of derivatives of the log of q results in a sum. Maybe it's a very large sum. It's an extensive sum, but those sums are all finite. I cannot get a discontinuous change if the little q's extend only over some finite region of a macroscopic system. This implies that not only do you have to have an infinite number of degrees of freedom, but you cannot break up that infinite number of degrees of freedom into non-interacting subregions. This is a macroscopic system. It would seem reasonable naively to imagine that I could consider microscopic fluctuations in one subregion a millimeter away from another subregion without having to worry about correlations that persist over there. However, this is telling us at a phase transition, it must be that correlations persist over those macroscopic scales. That's the only way to get a discontinuous behavior. And indeed, if we were to think back to that boiling transition, imagine the heat capacity as a function of the temperature. At boiling, we would see a discontinuous change in infinite heat capacity exactly at the boiling temperature. If I ask for the intensive heat capacity, I know that that's proportional to the mean squared fluctuations of the energy divided by N. That mean squared fluctuations of the energy can be written as a sum over local energies I less its average times local energies J less their average that gives me something that goes like N times N the self fluctuations of each individual cell plus N times N minus 1 number of pairs of cells, the correlations between the fluctuations in cell I and cell J. as n goes to infinity, CV over n goes like something intensive, the odd site fluctuations, which owing to the fact that there's a finite number of degrees of freedom in that quantity, will not diverge, plus n times the correlations in the fluctuations between different cells. So while this term is finite, this term, provided I and j are correlated, for all I and j, will diverge as n goes to infinity. It will go like n. A way to think about that joint fluctuation would be to imagine that I and j are separated by some distance rij, and even for large rij, large separations between cells I and j, those correlations must not average to 0. Otherwise, I will sum up something that has a prefactor that's getting large times 0 is something that remains finite. So in order to get an infinite heat capacity at a phase transition, like the boiling transition, I need not only a thermodynamic limit, such that this prefactor n gets large, but I need correlations to persist over the entire system, so that even though n is getting large, it's multiplying something which is finite. So this is another reflection of what we argued here, that to get divergences, to get true discontinuous changes, I need correlations to persist over macroscopic scales. This places some basic geometrical restrictions on what kind of phase transitions are possible. So consider, for example, a system which can become macroscopic in only one dimension. So imagine, if you will, we had some carbon nanotube, and we filled up that nanotube with some water. Put it in contact with its vapor. Let's call the width of that nanotube, give it a radius r, which is going to remain finite. Let's give it a length L. That could be taken as large as we want. And let's ask the question that if I was at conditions where the liquid and the vapor were thermodynamically at equilibrium with respect to each other. So the chemical potential between the liquid and the vapor were 0. Could we, in a one-dimensional system, actually support a phase transition that puts those two phases in contact with each other? Or when could an interface like this form to draw a distinction between these two phases? That's a terrible looking interface. A liquid is a distinct state of matter from its vapor in regions of the phase diagram where there's an interface that would separate the two if they're put in contact with each other. So a question one could ask is if in one dimension, such an interface would ever be stable. Well, what are the thermodynamics associated with such an interface if the chemical potentials of the liquid and vapor are the same, such that I can create some amount of vapor or create some amount of liquid with no thermodynamic penalty? All I can do is move that interface around. What is the free energy to create that interface? Well, the liquid molecules over here at the interface between the liquid and the vapor have broken bonds. They've lost interactions relative to what they would look like in the interior of that liquid. And thus there's an energetic penalty that those molecules face moving to the interface. So the free energy to create the interface will incur some energetic penalty that will go like the size of that interface. If this is a nanotube, that's something like pi r squared. But if I could put that interface anywhere, I've chosen to draw it right there. If I can move that interface around, there's a degeneracy, there's a multiplicity associated with the number of arrangements I could put the interface. And so there's an entropic benefit to forming an interface. There's a new mode that can fluctuate, a new number of ways of arranging the system, given I'm going to put an interface down. The entropy is something we can count. It's just the number of places I could put that interface. The log of that number, which is the log of L, KB log the degeneracy is the entropy. This is counting up space states with some little region L. Now, if we took the macroscopic limit, where R stays finite, but L gets infinitely large, what happens to this free energy difference? Delta G goes to minus infinity, meaning that it is thermodynamically favorable to create an interface. Which would mean that they are created spontaneously. And thus they would proliferate. We would form interfaces all over the place, which would destroy any distinction between the liquid and the vapor. I would form a liquid and liquid vapor interface here, and one here, and one here, and one there. I would make some liquid here. If I have no continuous liquid state separated from some continuous vapor state, I have no distinction between those two phases, and thus I have no phase transition that could exist to stabilize those two. This is essentially an argument due to Landau, which restricts the ability for a discrete transition, a discrete symmetry breaking, words that we'll flesh out briefly, from existing in one dimension. This should be qualified. This is away from T is equal to 0. If T is equal to 0, the entropic penalty doesn't matter. So I could stabilize an interface. It also requires that this delta E itself does not scale with the size of the system, which restricts the kinds of interactions that I'm considering with this argument. Namely, those are interactions which have finite extent. Turns out you can stabilize phase transitions in systems that have infinite ranged interactions, or at least large interactions that persist over large scales. There's a generalization due to Merman and Wagner. In 2 dimensions that precludes continuous symmetry breaking. Which is something we'll talk about in a couple lectures. Continuous symmetry breaking is like freezing. I pick a specific continuous direction to order along. Merman and Wagner say that this is impossible in 2 dimensions. Okay, so this is to remind you that when discussing phase transitions, dimensionality matters. One last little bit of phenomenology. Is the notion of universality. These are initially experimental observations that really make the study of phase transitions and critical points really compelling. For example, if we go back to our boiling transition, if I was going to look carefully at the density as a function of the temperature, we just talked about how as I increase the temperature, I will decrease the density. It will change discontinuously. If I construct a locus of those points, those discontinuous points, at different pressures, I will trace out a coexistence curve that ends in a critical point for which there's a critical density associated with it. So above that critical temperature, if I was going to play the same game, let's do it in black, increase the temperature and monitor the density, I would find a smooth transition rather than a discontinuous transition. If you go in and measure how exactly that density changes relative to that critical density, upon changing the temperature, you would find that it goes like a power law with an exponent beta. That's not Boltzmann's constant times temperature, but rather a number 0.32. Why am I telling you that? Because if I took a magnet, ask for its magnetization as a function of temperature, I would see the same sort of qualitative behavior. The magnetization goes down. As I say, tune a field, I go through discontinuous change. If I trace out those locus of coexistence, I have a coexistence curve, this centered at 0, also ending at a critical temperature. And if I were to measure how the magnetization goes away as I increase the temperature, we would find that it goes away like a power law, T less its critical point, with that exact same exponent. Which is then very surprising. I do two qualitatively different sorts of measurements, measure the magnetization as a function of temperature or the density as a function of temperature. Two very different sorts of phase behaviors are observed, demagnetization or the liquid vapor critical point. And yet quantitatively we observe analogous behavior, namely that the order parameter, the number that distinguishes the two phases, either the magnetization distinguishing spin up from spin down, or the density distinguishing a liquid from its vapor, and how those order parameters change with temperature near their critical points are with the same exact exponent. This is the notion of universality, that two distinct sorts of transitions can have underlying similarities, can exhibit universal properties. It's not limited to how the order parameters change. If I were to measure the susceptibility, so how the magnetization changes with an applied field, that too would go like a power law, T less Tc, with some other critical exponent gamma. If I ask analogously how the density changes with pressure, it would go like a power law with that same critical exponent. In this case, 1.2. So Landau theory is a way of unifying seemingly disparate phase transitions with a common theory. Before we develop it, let's take a remaining part of the class to understand how traditionally one might approach phase transitions using simple models. So because phase transitions arise because of collective behavior, these system-spanning correlations, it is very difficult, even in simple models, to study them analytically. So a number of approximate techniques have been developed to interrogate systems. And today we'll talk about one that you likely will have encountered before, so-called self-consistent mean field theory. And we'll do this in the context of a simple model of magnetization, so-called Ising model. So we will today work through a particle-based theory. We'll first write down a Hamiltonian for the Ising model and figure out how to approximate its partition function and uncover features of its phase transition. That should feel familiar to you because it's not unlike what you do in an introductory course. And in fact, it is exactly what we do in the introductory course I teach. That will serve as a bit of a bedrock for then moving that theory onto a field, which is what we'll do in Landau theory. So first, let's introduce the model we'll consider to understand magnetization. Ising's model. It's a minimal model for magnetization. Its Hamiltonian or energy function is given by a sum of two terms. One could apply a magnetic field H, which is conjugate to the total magnetization, which is given by the sum of spin variables. So let's imagine I have a lattice, and on that lattice, I have some spins that can point up or down, so-called easy axis magnet. Let's label those spins SI, which can be plus or minus 1, referring to if they're up or down. Summing over all those spins gives me the net magnetization. If half are up, half are down, I have 0 net magnetization. If all are up, I'll have N units of magnetization. So, as we talked at the top of the class, a phase transition will not exist unless there are correlations. The only way to generate correlations are through, or a way to generate correlations are through interaction. So we need an interacting term. So let's imagine that those spins can benefit from an exchange interaction. Which says that spin pairs like to point in the same direction. So this J is some exchange coupling that says that if spin I is up, it is favorable for spin J to be up. Because that J we're imagining to be positive. And let's put a prime on this sum to envision that only nearest neighbors interact. So on the square lattice, a tagged spin has 4 interactions to its north, south, east, and west. It's a minimal model. One could go beyond it by including longer range interactions, 2 and 3 body interactions if you really want, but what we would find is that largely those details won't matter. So this Hamiltonian, initially dreamt up by Mr. Ising as a graduate student, who subsequently solved exactly in 1 dimension and was really bummed out, quit academia because it didn't predict a phase transition. Little did he know, if he was able to solve it in 2D like Onsager did, subsequently it forms the kind of bedrock of the statistical mechanics of phase transitions. Okay, so that's the model. It's going to describe magnetization. One bit of phenomenology we likely haven't really stressed enough, but which comes through in considering Ising's model, is that phase transitions are intimately linked with symmetries. At h is equal to 0, this Hamiltonian, which is a function of a set of spins, has Z2 symmetry. It has an up-down symmetry. If I take a configuration of those spins and I flip all of them, the energy is left invariant. At finite h, that symmetry is broken, but along the h is equal to 0 line, I have that symmetry. Thus, we can anticipate that if I form a state where all the spins are up, that is a manifestation of a spontaneous symmetry breaking. And we'll see how that is borne out shortly. If I wanted to take that model and try to compute the partition function, well, I know how I would write it down. It would be a sum over S1 being plus or minus 1, a sum over S2 being plus or minus 1, all over 2Sn being plus or minus 1. I'd have an exponential of minus becomes a plus beta j si sj. Here's neighbor interactions, and if I had a finite field, there it would be. This is hard because of this interacting term here. It means I cannot factorize that sum. I cannot simply evaluate the partition function. The statistics of spin I depend on the state of spin j, and so on and so forth, making it almost intractable. It is tractable in 2 dimensions and in 1 dimension, but it's cumbersome to do it then. So rather than trying to solve this partition function exactly, we could try to approximately solve it. So a standard means for approximating an interacting system like this would be to apply a mean field theory. Namely, we could write the Hamiltonian with an effective field, H effective, conjugate to the spin variables, where this effective field has the original external field, but in addition, J times the neighboring spins of I. The picture here being that I take a spin in contact with its neighbors, and I envision thinking about what that spin does in a field generated from the external field in addition to its neighbors. That rewriting by itself is not an approximation, but if we approximate the fluctuating field, fluctuating as the spin j's change, with its average, that will become a single spin theory that we can solve. So the average field that this tag spin feels is its external field plus J Z, Z being the number of neighbors that that tag spin has, and the average value of the spin. All neighbors are equivalent, so we just have the coordination number, how many spins there are, times the average. Where this is, we could call it little m, which is average big N over big M over big N. That is the mean field approximation, and it renders the partition function solvable. Because now I have a sum over all of my spins, S1 to Sn, e to the minus plus beta h effective, summed over all of the spins. I can associate each member of that sum with its own sum over its microstates, yielding n factors of a single spin partition function, where the single spin partition function just sums over the two values that a particular spin can have, e to the minus plus beta h effective spin, which is twice the hyperbolic cosine of beta h effective. Or, putting in what we mean by that h effective, h external plus jz little m. Now, little m, the average spin of the neighbors, the average value of the spins of the neighbors, is an unknown parameter thus far. If we took the derivative of log of q with respect to beta h, that would pull down the average magnetization of the tagged spin if I took the explicit derivative from the single spin partition function we just computed, that gives me the derivative of hyperbolic cosine, which is hyperbolic tangent. Oops, that's my betas. Beta h plus beta j z m. I now arrive at a self-consistent expression for the average magnetization. So the physics here is that we imagined replacing a fluctuating environment for a single spin by just its average. That average depends on the average value of the neighboring spins. Thermodynamic consistency means that the derivative of log of little q with respect to beta h is the average magnetization of the tagged spin. If I say that all spins are equivalent, that then gives me a self-consistent expression for the average magnetization. If I imagine that m is small, which will be true near the critical point, where the magnetization goes away. Remember, it went away. If you put your fidget spinner in the microwave, you lose the magnetization. It goes away like a power law, phenomenologically. So in the vicinity of a critical point, m is small, I can imagine Taylor expanding the hyperbolic tangent at 0 applied field. So I have m is approximately equal to beta j z m. That's to first order. Hyperbolic tangent is an odd function, so the second order term vanishes. The third order term, be beta jz quantity cubed m third. That is satisfied for m is equal to 0. As well as plus or minus of a quadratic equation, two different values whose solutions will depend on what beta jz are. So if beta jz is greater than 1, less than 1, I will only have that single root. If it's greater than 1, I'll have this degenerate solution. So we have essentially discovered a critical temperature, beta jz over kb. One could see this explicitly by plotting m is equal to m and the cubic polynomial, which for beta jz less than 1 has only one root. but we'll have 2 roots otherwise. So as we go between 1 solution and 2 solutions, that is manifesting the symmetry breaking associated with 2 degenerate finite M solutions. So it's sensible to call that the critical point. Replacing beta JZ with TC, we find that those 2 solutions go like T less TC over TC times a factor of 3, implying a critical exponent of 1/2. So these are the sorts of arguments we elaborate on in introductory classes, so I've done them somewhat quickly here, but it tells you that mean field theory is sufficient to illustrate spontaneous symmetry breaking. But the exponent is not quite right. This is all a very microscopic perspective on this phase transition. An alternative to the microscopic mean field theory would be to just use simpler thermodynamic arguments. So this will be more in line with what Landau theory does. And so let's explore this in the remaining 10 minutes of class. So we've been working with an ensemble, a partition function, which depended on things like beta, the applied magnetic field, H, and the number of spins. So it's a natural function of beta, H, and N. That's kind of like saying that we were working in an ensemble for which the relevant auxiliary function, the relative thermodynamic function, is like the Gibbs free energy, which is a natural function of the mechanical variables that I'm manipulating the system with, in this case, an external magnetic field. Now we know from thermodynamics that the Gibbs free energy is related to a Helmholtz free energy through a Legendre transform. So if we let F be the Helmholtz free energy, we could recover that by adding to the Gibbs free energy H times M, where the partial derivative of the Helmholtz free energy with respect to the magnetization at fixed T and H, not T and H, T and N, is the magnetic field, or is the applied field. So provided we are close to the critical point, one might imagine that we could Taylor expand the Helmholtz free energy. It's a natural function of the magnetization, and as a series in that magnetization. That would assume that the Helmholtz free energy is smooth, which is not going to be in the thermodynamic limit. Nevertheless, we could proceed and see what we get. So a natural function f of m, let's do it intensively, would be some 0th order term, F naught, plus some 1st order term, F1, multiplying little m. 2nd order term, F2, m squared. Some 3rd order term, F3, m cubed. 4, m4, and we could go on. Now, if we were at 0 applied field, we need to preserve up-down symmetry. That would mean that F, this natural function of the magnetization, is equal to F evaluated at minus m, which means that F would have to be an even function of m. The 0 of free energy doesn't matter, so let's get rid of it. All odd terms have to go away. And so we are left with a free energy density functional, that is parameterized by 2 terms. Let's go ahead and give these 2, 6, 4. Some F2 and some F4. Those are expansion coefficients. They are derivatives of the free energy with respect to the magnetization. We could find the average value of the magnetization by minimizing the free energy. So what would that look like? dF divided by n dm. That gives me F2 times m plus F4 times m cubed. Extremize, so setting it equal to 0. The average value of the magnetization is 0 if F2 and F4 are greater than 0, and is equal to plus or minus negative F2 over F4 square root of if F2 is negative and F4 positive. Does that look familiar? Indeed, that's the same fractional dependence, functional dependence that we found from the microscopic mean field theory, that the magnetization will grow like the square root of some number if we further expanded F2 to be an expansion in the temperature near the critical temperature. It would have some expansion coefficient, call it A, to first order in the temperature difference, T less Tc. We could define a little t as T less Tc divided by Tc, and assume that F4 is just a constant. We'll have m is equal to plus or minus a negative t over F4 square root of if little t is less than 0. Implying a critical exponent of 1/2, just as we got from a more sophisticated mean field theory. This route, however, just postulated some basic symmetries. So at 0h, we assume that locally we could develop an expansion of a free energy in terms of this magnetization, an order parameter for distinguishing the two phases, doing that expansion and phenomenologically parameterizing it with some temperature dependence to low order. We find that that polynomial expansion for little t less than 0 supports two basins. That's what that fourth order polynomial would mean. For little t above 0, we would have a single solution at 0. And in between, we would have a vanishing second derivative of the free energy bounded as long as F4 were positive by a quartic polynomial. So we get the same macroscopic observables, the same phenomenology in this very simple model for the free energy functional as a function of that order parameter, as we did when we did a mean field theory, starting from a microscopic Hamiltonian. So it's really the latter that Landau theory postulates. However, in the specific case, the Eisen model will show that one can actually derive this phenomenological low order expansion model from the underlying microscopic degrees of freedom. But really what is important is just that that specific phase transition implies a symmetry group, which constrains or simplifies that free energy function. All right, so we'll explore that more in the upcoming lectures, and we'll actually be able to make some pretty good progress with understanding the limits of mean field theory as we put this free energy functional on an actual fluctuating continuous field. We'll be able to work out properties of defects and boundaries and interfaces on that field and extend notions of second order transitions and accommodate in a more natural way than is really possible with discrete models first order transitions and even fluctuation induced first order transitions, where fluctuations play an intimate role in converting a seemingly second order transition to a first order transition. Such things happen when systems order at finite wave vector, like one sees in block copolymer nuts. Okay, so stay tuned for all that. Look forward to seeing you all in the small groups, and I hope